So now we can write down this double integral for a function of two variables. Remember, we're integrating over a rectangle R in the xy plane. And we believe that this thing is the volume of some surface underneath some surface. But what do we do with this? How can we do any kind of calculation with this thing? Well, the key is to remember that this dA here is a little patch of area. Right? So we're adding up over all these little patches of area. And so it seems reasonable to say that dA is dx times dy. After all, if it's shaped like a box, then the width times the height ought to give the area. So we can write down our double integral as an integral dx dy. And once we do that, it suggests a strategy that we work our way from the inside out. So we can write this as an integral with respect to dx first, and then an integral with respect to y. When you write it this way, on this inside integral, right, we're integrating in the x variable first, and x goes from a to b. On the outside integral, we're integrating in y, and y goes from c to d. So this is called an iterated integral. We might just as well have called them partial integrals, right? This term here is an integral in x, so integrate in x with y constant. Right? That's the way we took partial derivatives as well. Once we do that, right, we get some integral, we get some number, right? A definite integral is just a number, but the number that we get depends on y. So in fact, we get g of y. So what we're left with is then the integral of g of y dy from c to d, and now you integrate in y. So you see what happens when we integrate in a variable like x. You integrate that variable out, just as you do with an ordinary single integral. Then all that's left is the y. Then we integrate out the y, and what's left is a number.